Okay, in this video I'm going to finish off exercise 7a of the book Fundamental Applied Mathematics. We're on page 172 and the question is 13. So it reads, two particles of masses m and 3m are connected by a light rigid rod. The system rests on a smooth horizontal table, the heavier mass due east of the lighter mass. The heavier mass is projected with initial velocity of uj hat. Find the velocities of the particles when the rod runs north-south. Note, when the rod runs north-south, the j component of both velocities must be equal. This is actually quite a tricky question. So what I've done is, I've just worked ahead a small bit. I've drawn, of course, a sketch of the motion. I've drawn in their initial velocity vectors. So of course the small mass m has no velocity. The larger mass is just a j component of its velocity. Then I've applied the principle of conservation of momentum here. Alright, the only thing to note here is that we don't know what the velocity vectors of both masses are at any time really. So I'm going to call them x and y and p and q. However, when it's north-south, the two velocity vectors in the j component direction are equal. So I have x plus q and p plus q. Next, if you compare the j hat directions, you're going to get that 3m times u plus m times q plus 3n times q is equal to that. So basically, if you just rearrange it, you're going to get that q is equal to 3/4 u. Similarly, you're going to get x equal to negative 3p if you compare the I hat directions. Now the thing is, that's not the difficult part. The difficult part is working out how to get an expression for either x or p in terms of u. That's quite difficult. So I thought to myself, what about a change in momentum? In other words, an impulse. So I said, if the impulse imparted by the 3m mass on the rod, it must be equal to the impulse imparted on the small mass, okay, because the small mass is part of the rod. So the first thing I'm going to do, is to calculate the impulse imparted by the 3m mass. So impulse is equal to the change in momentum. So we're going to have 3m times, and it's going to be pi hat plus qj hat, and we need to take away from that uj hat. And I'm going to call that impulse number 1. Now I'm going to calculate the impulse imparted by on the small mass. Okay, the small mass up here. So that's going to be m times xi hat plus qj hat, and that's it. There's nothing to take away because the rest is 0. And I'm saying that the two of those must be equal. So let's just do that. Of course the m's are going to cancel. So we're going to get 3 outside of p plus we'll say pi hat plus q minus u j hat is equal to xi hat plus q j hat. The next thing I'm going to do is substitute in values which we've already worked out. We know that x is equal to negative 3p. Alright? So I'm going to call this negative 3p. Like so. We know that q is equal to 3/4 u. Like so. Like so. Alright, so now let's multiply in by 3. So we get 3 pi hat. And this, by the way, so 3u, so this just becomes negative 1/4 u. 3/4 minus 4/4 is negative 1/4 u. So it's going to be negative u over 4 j hat. Like so. Multiplying in by 3, we're going to get negative 3u over 4 j hat is equal to negative 3 pi hat plus 3u over 4 j hat. So bring the p's across, and we're going to get 6 pi hat is equal to 9u over 4 j hat. Alright, so drop down the 6 and we're going to get pi hat is equal to, and we're going to get, one sec there now, 3u over here and a 6 down here. Alright, so that's equal to u over 2. So u over 2 is equal to p. But we know that p is equal to, we know that x is equal to negative 3p. So what can we write? Just bear with me now, and I'm going to rewrite this. So p is equal to u over 2. Alright, we're doing well. That's the end of the question essentially. So if p is equal to u over 2, alright, and we know that we'll say negative x over 3 is equal to p. So if we just multiply that by 3, we're going to get what x is. So x is going to be 3, one sec there now, 3u over 2. Wait, was there... It's not half, there's a fucking quarter at it.